Let me introduce Tarun, a business development manager for the specific product line that we are going to talk about. Tarun, please introduce the product and help us understand it better.
Not often it happens that technology companies invest 16% of their revenue back into research and development. And not often it happens that technology companies in a changing dynamic environment keep a roadmap, a plan ready to introducing better products and work on newer technologies. National Instruments over the year has introduced lot more, every year it has introduced products based on better technologies which have improved the way scientists and engineers have been making measurements or building embedded systems. We are very proud to announce this year the world's first vector signal transceiver. Vector signal transceiver is a combination of a vector signal generator, a vector signal analyzer, and a processor board, a completely programmable processor board in a small form factor of a single module of a PXI form factor. Vector signal transceiver, as I mentioned, is a 3U module. It occupies 3 slots of a PXI Express chassis and has and can serve as independent vector signal analyzer or receiver, vector signal analyzer or vector signal generator. It also has a programmable FPGA which can be used for making custom measurements. Vector signal transceiver has a frequency range of up to 6 gigahertz and has a real-time bandwidth of up to 80 megahertz. This covers virtually all existing wireless standards and even some of the emerging ones like 802.11 AC. As you can see, in a 4U PXI, in a 4-slot PXI chassis, we can fit in a vector signal transceiver. It is really a very compact form factor, and this has been made possible by some very by patented technologies from NI Research and Development, like advanced calibration, like wideband digital correction, etc. Okay? And this module not only has these capabilities, but it also can extend these capabilities to many other modules. For example, the generation and the acquisition chains on this module expose the local oscillators outside. So they can take the local oscillators from external modules, or they can export the local oscillator to the external modules. This allows us the capability to integrate multiple of these modules in the same chassis. I can share the local oscillators between these modules and make a multi-channel phase coherent system. Imagine a 4U chassis, 19-inch rack mountable, and you have 5x5 MIMO chain within this form factor, with each module having its own user programmable FPGA. It's really power packed. And with all these features, okay, it is not difficult to program this module as well. Okay. Those who are familiar with the LabVIEW platform, VST comes along with LabVIEW APIs with which you can program it for individual operations of its modules or as a combined functionality. Besides that, for traditional users, you have software panels, okay? But the best benefit of VST comes along with the driver APIs or the LabVIEW APIs, which allow you not only to use the existing toolkits like GSM, CDMA, or WLAN wireless LAN measurement toolkit suite, or WiMAX set of suites, or LT toolkits. Okay? But at the same time, the drivers are open, the APIs are open, and you can really drill down to the base of the code and can actually reach the pins, hardware pins, and program them. Okay? This is a paradigm shift from the box instruments where the functionality is predefined. Okay? In these instruments, you can really make the customization to the hardware pins, and that's why we call it as a software design instrumentation. Let me show you a small video which summarizes some of the capabilities of this instrument.
Graphical system design and fitting it onto the software designed instrument. Should we get onto that?
Yes. Before we go to the demo, Satish,
Sure.
let me take some more examples just to elaborate the concept. Let's take an example of 802.11 AC chipset. John had earlier shown this in his slides earlier. As John mentioned, 802.11 AC chipset has lot of permutations and combinations of the components on the chipset. Okay, you can choose different types of modulations. You can choose different levels of power settings and frequency settings. Okay, this becomes a nightmare for the test engineers. Okay, all these permutation combinations, if they need to test, okay, it increases the test timings tremendously. Okay, now to constrain these test times, okay, often the test engineers have to go down lower on the combinations of settings that they can test. They may not be able to test either all modulation types, or they may not be able to choose all the frequency steps or the power steps that they may like to test. This results in insufficient testing, or rather validation which has a lot of approximation and assumptions built in. Okay, validation which is not foolproof, right? A major benefit of instrument like VST, okay, which combines or which has the control on the FPGA itself for the instrument, okay, which allows you to very quickly change the hardware settings of the instrument. It allows you to test the to conduct these tests in a very, very short time frame as compared to the traditional instruments. And this brings in the flexibility of testing it over multiple points, okay, with very, very fine resolutions and doing a comprehensive validation of these chipsets. So as you can see, the density at which, or the resolution at which the chipset can now be tested is far more. Okay. This is one of the big benefits or a unique value point of having a software-defined system. Okay. As you can see, again, this is how the system used to be earlier, traditional instruments. Those who are familiar with the PXI platform know that PXI makes the testing much, much faster. But with the introduction of a platform which has the instruments combined along with the FPGA, you can get much higher productivity gains, okay, almost 200 times better than your traditional instruments. So enough of talking. Let's see some examples, some live demonstration of how this instrument works.
Okay, so you're going to give it to me now?
Yes.
Okay. So I was planning to give the demo to him. Now he's just pushing it on to me. Okay, so let me quickly take you through this demo. I have a power amplifier which I'm going to test. So here's the power amplifier that's connected to the world's first software designed instrument, which is our vector signal transceiver. Now, at the same time, we need to keep ensuring that the input voltage level is maintained. Okay? So there is some PID or closed loop control that has to be done on this side. The traditional approach to do it is to have an engineer sit there and give the power at one level, see the measurement, and if there is a dip in the input power, he needs to correct it, and then again go back and take the measurement. And you can see how quickly it's moving. And this is possible not with any other instrument, but for the vector signal transceiver. I'm going to give you a quick comparison of what is it on a traditional instrument to what it is on the vector signal transceiver. Do you see a line here? That is roughly around 4 minutes to do this particular measurement using a traditional instrument. Now I'm going to quickly show you how much time it takes to do it using the vector signal transceiver. Do you see any other lines? You don't see any other lines, right? So let me zoom in so that you can clearly see how much time we are taking to do these measurements. So here's my zooming tool on LabVIEW, and I'm zooming in. So here is how much time we take. It's around 5 milliseconds. So 5 milliseconds is the time that we are taking now to do this measurement, from what it used to be on the traditional instrument to what it is on the vector signal transceiver. It is close to a 800x improvisation that has happened. It's an 800x improvisation, right? So think about the amount of tests that you could do, the amount of validations that you could do using this platform and making sure that these products deliver the required performance wherever needed. Now, getting back to the same discussion, Tarun, that you were having, you were mentioning about 3 different levels of software. Can you explain that in detail? If I'm an engineer who's just using a traditional instrument, can I use the vector signal transceiver?
Sure. So vector signal transceiver, as I told you, comes along with layers of software or levels of software. For users who have been using these traditional instruments or who are very familiar with the displays of the traditional instruments, it comes along with the soft front panels. Now, the soft front panels are available for different toolkits for different wireless standards or for simple physical RF measurements like spectrum analysis and modulation measurements.
Okay, so I can use them as traditional instruments. Can I use them as software-defined instruments? Like we used to do that with the older PXI modules, right? So is that still possible?
Yes. The old drivers or the form of the same old drivers is available with the VST as well. So LabVIEW APIs allow you to use the vector signal transceiver functionality in LabVIEW program, in the floating point programs. Okay. Having an FPGA on board does not mean that you have to program the FPGAs all the time. Okay. The FPGAs sometimes or with some of the functionality is pre-programmed by National Instruments. But at the same time, having said that, these drivers or these APIs are open. You can actually go down to the FPGA codes and customize them. In fact,
does that mean I can put my own algorithms onto the instrument?
Right, Satish.
Wow, that's amazing.
In fact, you can have your own VHDL or FPGA, LabVIEW FPGA codes, which you can put onto these onto this FPGA and actually program the hardware, okay, the hardware pins of the module.
Okay, so that means this instrument can be programmed at 3 different levels. One is as a traditional instrument, you could use it. You could use it in the next level, which is using the API. So you could quickly replace whatever instrument you've been using and use this instrument. And the third is to get in deeper to make sure the functionality is defined. So does this, in your experience, help us reach out to a lot of new application areas? I know you've been working a lot on defense, so can you share some insights on that?
Certainly, Satish. So this brings us a lot more capabilities in hands of scientists and engineers. Okay, not just you will observe that not just we can integrate or control our acquisition and generation using the hardware. For example, you can use frequency scan list or power scan lists. You can use onboard triggering. You can do an intelligent detection of a signal. So not every signal is worth processing. So you will wait for the right signal to come, and this selection of the right signal can be a FPGA algorithm. So once you have it, your acquisition module will start sending the signal onto the board only when the right instance has come. Okay. So these are all controlling the acquisition. And similarly, you can make your customized measurements, or you can extract information from the signal on the FPGA. Very similar is your transmitter processing. So you have the hardware, okay, but what you need to generate can sometimes be based on the input signal. So changing the output signal depending on what the inputs the user is getting, okay, requires real-time embedded processing. Okay, and that's what is now possible on this particular module. VST actually completes our ecosystem of RF system design. Okay, we have VSAs, vector signal analyzers, vector signal generators, and FPGA-based processor boards, and all of them can be seamlessly integrated along with the software tools, okay, to provide a comprehensive system for designing embedded RF systems. Okay, let me take you to some example cases. Okay, just a brief synopsis of the capabilities of the module. Software-defined radio testing is a very complicated task. Okay, software-defined relies on, or the nature it is software-defined is, it relies on the processor itself to change the communication method, okay, if the channel is changing, right. So if you have to test a software-defined radio platform, you need to have a system which can change the channel conditions dynamically. And such a testing is very much possible now with the vector signal transceiver. Okay? You can have your transmitter channel, receiver channel connected to the corresponding channels of the VST, and on the FPGA module, you can have your modulation schemes programmed and your channel programmed. Now, this channel can be as simple as AWGN, Doppler, multipath, or you can have comprehensive models like fading models or terrain model or antenna patterns programmed onto the FPGA. And as the user requires, the channel can keep changing and you can observe how the SDR is behaving. Is it changing the modulation schemes or the data rates as per the channel conditions? So that's one very unique application which is made possible by a product like this. Let me give you another example. Those who work in the radar domain often get to use radar target simulators. Radar target simulator, the very important functionality that is required is your input and output channels have to be phase synchronized. Okay? Vector signal transceiver allows you to do that. As you can see, I can share the local oscillator of the input chain with the local for the output chain as well. So I can have a common local oscillator for both input and output chains. So that ensures phase synchronization between input and output channels. And again, now on my FPGA, I can program my target parameters like range fading or Doppler or even clutter and false alarms.
So Tarun, you're saying that this can be used as an embedded product?
Yes, very much. So once the FPGA has been programmed with the required functionality and I have a real-time operating system running on my host, I can have the complete system run as a headless unit. In fact, you can just switch it on and you can have a display just like a traditional embedded box.
Okay, so that's interesting. So this platform, the vector signal transceiver, is just not an instrument. It can also be used for building some amazing RF embedded systems. So that's a really valuable insight. Thank you so much, Tarun, for joining us, and looking forward to having a lot of interactions with the customers here.
Thank you.